Hello everyone, my name is Mocinaldo. I am a student of Computer Engineering at UFRN, and I'm here today to present to you a framework for efficient communication in IoT applications in the automotive industry with OBD-II Edge. On this slide, we can see all the authors of this work, and as the main author, I will present the work to you. In this sense, I will contextualize the work, show the proposed approach, the case study, discuss the results obtained, and finally, the conclusions. The rapid advancements in Internet of Things technologies and the proliferation of connected devices have paved the way for deep transformations in various industries. One industry that experienced a profound impact with this is the automotive industry. Vehicles have evolved into intelligent and interconnected systems capable of generating vast amounts of data through an array of sensors and devices. As a result, cars have become increasingly intelligent and are now seen not just as a means of transport but as a development platform on which you can extract value from the data generated. It is possible to carry out analysis ranging from engine performance to driver behavior. But how can we extract information from sensors? This is done through the Onboard Diagnostic System, or OBD, specifically the OBD-II protocol, which requests information from sensors to the Engine Control Unit, or SCU. This protocol is open and consists of a standardization of the communication protocol for vehicle diagnostics. To carry out this communication, it is possible to observe in the literature the wide use of these two types of hardware, which are dependent on a smartphone. In other words, this hardware is plugged into the car and connected to the smartphone via Bluetooth. The smartphone receives the data and sends it to the cloud via Wi-Fi or 4G. Our proposal based on the Internet of Things uses this third hardware and is based on the OBD-II Edge. Specifically, this model is called Freematics 1 Plus and has an ESP32 based microcontroller programmable in C or C++ language and completely open source. Furthermore, it has an integrated Bluetooth module, Wi-Fi, 4G, accelerometer, GNSS antenna, and SD card for data storage. The set of these functionalities allows this hardware to capture data from the vehicle's ECU, perform processing at the edge of the network in real time, and send this information to a server completely independently of a smartphone. But it's not just about collecting the data. The abundance of vehicular data presents unique challenges regarding efficient communication, processing, and storage, as well as consuming this data to perform analysis. Handling the influx of data generated by intelligent vehicles requires sophisticated data management solutions that can scale to meet the demands of modern IoT applications. To address these challenges, adopting robust data storage platforms has become highly desired. In this way, our work proposes a framework for efficient communication in IoT applications in the automotive industry that covers the entire process, from data collection at the edge to interactive visualization. So our proposed approach is divided into three parts with 6 components in total. The first step is vehicle connective and data capture, that is, Freematics 1 Plus connected to the vehicle at the edge. As mentioned previously, it is programmable in C or C++ language, and the code is embedded in the hardware with the platform I/O plugin. The second part is the architecture module, which is composed by these 4 components. First, we have data preprocessing and production, because the data sent by Freematics is of the key value type, with the key in the hexadecimal value of the PID and the value already formatted for the final unit. For example, RPM it sends 10C and 2000. Speed it sends 10D and 60, and so on. To address this, the Node-RED tool was used, which makes it possible to build services and applications related to the IoT domain and offers an interactive interface with nodes and flows, thus facilitating the organization of the data and enabling connections with other services, databases, and applications programming interfaces, or APIs. In this sense, this tool captures data from Freematics and performs some processing such as renaming keys and removing possible new values. Furthermore, the data is structured in JSON format and finally pasted to Apache Kafka in the event streaming module. This tool is a publish-subscribe messaging system commonly used as an intermediary in various applications, with the main objective of collecting and transmitting substantial amounts of data with minimal latency. Its main function in the proposed approach is to receive data from the previous module and store it in a queue to mitigate the risk of server overload and ensure data integrity. The data consumer module is executed on the Node-RED server, and its purpose is to retrieve information in JSON format previously stored in a queue in Apache Kafka and then store it into the database. This process requires creating a structured query language script, or SQL script, on the server itself to ensure the proper formatting of the data when storing it to the timescale DB in the data storage module. This database is built on PostgreSQL due to its impressive scalability and automated management capabilities. This choice was driven by the requirement to analyze sensor behavior over time within the context of vehicle data collection, necessitating a database explicitly tailored for time series storage. Finally, the third part is composed of data visualization, which is done using Streamlit, an open-source Python library for creating webbing applications for data science and machine learning projects. With the Freematics 1 Plus ID, trip date, and the start and end times, the user can see some graphs from the trip. Some of these graphs will be shown after the case study slides. It's essential to underscore that the organization of these modules involved utilizing two Linux virtual machines, each orchestrated within Docker containers. The initial machine, denoted as the architecture module, is crucial in overseeing data collection, processing, and storage. On the other hand, the second machine, referred to as the application module, is specifically dedicated to managing the data visualization aspect. To evaluate the feasibility of the proposed framework, a volunteer who used a round-of-fit vehicle model 2012 with a 1.6 liters engine and manual transmission was selected. Next, the instrumentation was defined, which involved configuring the environment for the collecting data from this vehicle. In this case, Visual Studio Code and the Platform I/O plugin were used. Once this was installed, Freematics source code was downloaded from the official GitHub repository and configured by following these steps. Server configuration, where we defined the endpoint to receive the data. Communication protocol configuration, in this case 4G was selected instead of Wi-Fi, once in-track Wi-Fi is not available all the time. PID's configuration, it's which sensors were collected. In this case, there were collected fuel level, speed, throttle position, engine load, fuel pressure, timing advance, coolant temperature, and intake temperature. All these sensors are collected and processed every 1 second. Finally, data storage configuration. The hardware allows you to store information on the SD card and send the data to the server. So it was configured to perform both in order to maintain the data redundancy and assess whether any data was lost during sending to the server. After configuring the data collection settings, the route to be taken by the volunteer driver was defined. The route was chosen in the city of Natal, Brazil, which was previously familiar to the participants. That route is approximately 7 kilometers long and it consists of all paved sections. The period between 11:30 and 12 was selected for executing the route mostly due to traffic reasons. In the end, 390 data samples were obtained, being stored in the database for the route. Once the route was completed, the data was visualized with the Streamlit application. In this figure, it is possible to observe the time series of the throttle position along the route, and with this, valuable information can be extracted about the driver's behavior over time, allowing the analysis of acceleration and deceleration patterns. For example, in this case, the driver does not hold the accelerator position constant for a long time. He presses and releases it many times and quickly over time during this period. In this other one, he steps a lot and lets go very quickly. Then he steps a lot again soon after. This could be an indicator that the driver was behaving more aggressively, for example. Furthermore, it is possible to detect prolonged stops on specific stretches, among other analyses. In this figure, we can see the time series of speed and acceleration. On this side are the speed values in kilometers per hour, and on this other side are the acceleration values in meters per second squared. This type of graph is interesting because it allows you to assess whether the drive is accelerating the engine excessively, leading to increased fuel consumption and environmental pollution. It also allows the detection of sudden accelerations or braking and driving at excessively high speeds. In this case, in some sections the drive exceeded 80 km per hour and also made several deceleration and accelerations. This may be due to the speed bumps and crosswalks present along the route. By analyzing speed and acceleration data, you can better understand the driver behavior and driving habits. This information can be instrumental in promoting fuel-efficient and environmentally friendly driving practices and improving overall vehicle safety. Additionally, it provides valuable information to identify potential problems or areas for improvement in vehicle maintenance and performance. At left, it is possible to observe the route captured by the OBD-II Edge device and the variation in speed along the route. From this bar, it is possible to see that there are some range of values and that the color of the point varies according to the color of the range. At right, it is possible to observe the radar graph of RPM, speed, throttle position, and engine load, in which it is possible to calculate the area of the figure, defining an indicator and estimating the use of the vehicle's resources along the route. With this, it is possible to evaluate drivers' behaviors and determine different aggressive, moderate, and cautious profiles. All these graphs shows that the communication between the device and the platform was successful and that the data read from the sensors was not lost while the vehicle powered the device, since they are stored in the internal buffer. Although there were losses, the location there were insignificant in relation to the whole, given that the route taken is very legible. So, in this work, we proposed a framework composed of a server, database, and transmission procedures designed to analyze vehicular data using the OBD-II Edge device. A case study was conducted in a real-world scenario to investigate the proposal's feasibility in terms of sensor storage. The results indicated the feasibility of the proposal, contributing to availability of the automotive data analysis in a different way from previous works in the literature. Collecting data at the edge of the network using Internet of Things technologies opens up possibilities of carrying out real-time processing on low energy cost hardware. And having a framework that guarantees data integrity is of fundamental importance for scaling experiments. Feature works encompass a range of tasks to enable enhanced processing of vehicular data. The sample size of the case studies will be increased, covering more vehicles and routes. It will carry out new experiments with embedded algorithms for performance evaluation. Thanks to CNPq agency like this process number, which has helped us produce research and contribute to the development of science in Brazil. Finally, our contact details are here, and follow our research group on social media to see progress in our research. And thank you very much for your attention.